Alright. I think we're recording. I think we have audio and video and all that sort of stuff. Alright, any questions to start with? All right. Well, I said we would do more with tree insertion. We went through this quickly yesterday, and let me go through it in more detail today. And I seem to have really bad lag. Any chance PA3's deadline gets pushed back? Probably not. And you're having particular issues? Or questions or things you want to talk about with PA3? I'm going to have to change my window here. There's 2 or 3 midterms on Friday. And a project. So yeah, I know that's all kind of an alignment of planets thing. But if you, my anticipation was one would start the programming assignment, last week, and probably have it, done before things got on too far this week, and then could concentrate on exams. And the exams, I'm not sure you need to do a lot of studying for 222. I mean, mostly you want to be up to speed on the things you've been doing this quarter so far. Maybe do a bit of review on if there was an ODP that was a little confusing, but in general, you should be prepared already for it. I'm not gonna ask you to memorize, a bunch of things or stuff like that. It's mostly doing what you've been doing, so I hope it's not something that's going to take a lot of preparation for people. Unlike trying to get my video camera to work, which apparently we do not have the technology. Alright, so I'm going to do this. We're going old school again. All right, so we'll just run without a video camera. All right, so let's go back to trees, and I said we would write some code. So sometimes code helps clarify things, sometimes not. When I was taking data structures and algorithms and things like that, when I would see too much pseudocode, my brain would kind of gloss over, and I'm sure it made sense to the author who wrote it, but it didn't seem to help me with understanding what the algorithm was actually doing. So let's write some actual code for declaring a node and playing around with insert and maybe some printing and so on. And when you do your next programming assignment and we're implementing trees, this is not how we're going to do it. Okay, we're going to be doing it in a much slicker modern way, so I'm not giving away any secrets here. So let's do some stuff. And I'm not going to write this the way that I want you to write your code. I'm not going to put in, you know, all the commenting that I would like for something you were actually submitting, you know, or turning over to someone. And I'm not going to break it into separate files and that kind of stuff. I want to just kind of get to the code itself. So you may see some bad habits in here, so don't you know, throw away all the good habits that you've had. So let's make a tree node. So we'll have a tree node which contains some data and a left child and a right child. And let's make a root. So T node is root. You know what? I'm gonna do a type def. So I'll do a T node for a struct T node. I'm not going to make my type a pointer to a struct T node because I want to see these pointers in my code so I know what's a pointer, what's not a pointer. So I'm just going to type def a struct T node to be a T node. So what is root? That's the root of the tree. And an empty tree means the root is null. So our empty tree has root equal to null. And let's add some stuff to the tree. Alright, so I'm going to insert 5 numbers into the tree, build it up into a tree-like structure. So we looked at this idea of, you know, here's what your tree looks like to begin with, maybe. And when you want to insert something, you start here and you move either right or left until you get to a spot where you would like to move one way, but there's nothing hanging off of that. The child is null. And so you've created a new node somewhere. And the idea is, whichever way you want to go that's currently pointing to null, you just change that to point to your new node. Okay, that's our insert routine for today. And at the end of class, we were talking about this business of dealing with an empty tree. So let me do that at the end here. Let's look at our basic insert code here. So you're going to basically do a search algorithm here. So if, let me do a temporary also. We can use root to move through the tree if we want, but I'm just going to make a temporary that points to the root, and then let's let's go ahead and figure out where to insert it. So first thing I want to do, I want to look at the current node. So this is temp. So I want to look at that node's data and compare it to the number that I'm trying to insert. So I'm going to say if temp arrow data is bigger than num. Well, if the root node is bigger than what we're trying to insert, then num must go to the left. If we can move to the left, we will. But if there's nothing to the left of this node, but that's where our number needs to go, this is where we're going to insert. Okay, so we're going to say if the root node's data is bigger than our number, then we want to move to the left. Let me do it like this. So if our number is smaller than the root, we're going to try to move to the left. If there's nothing on the left, then what should we do? Let's just set the left child to be our new node. And let's return. Otherwise, if there is something to the left, let's move that to our temporary root and keep moving down the tree. Otherwise, we're going to move to the right. So if the right child is null, we should add our node there. So let's set temp right equal to our new node and return. Otherwise, move down the tree, so set temp equal to temp right. And so this is the end of our forever loop. And our loop's an infinite loop because we're going to exit, at one of these spots after we've created our new node, after we've attached our new node to the tree. Alright, so I have this variable new node that I haven't declared anywhere. This is the node that we want to insert. So we'll allocate space for it. And we'll set the left and right children to be null. And we'll set the data to the number that we're trying to insert. So now we got a node. Alright, so what's happening here? This is our temporary, which is also our root. Here's our new node, which is, 14. And let's say this is 10 and 15, or 50, I guess, and 11 and 5 and 70. And here's the node we want to insert. So we're going to come into our loop, and we're going to compare our number 14 to temp data. Well, temp data is 10, 14 is bigger than 10. So if it's less than it, we're going to do all of this stuff. Otherwise, we're going to do this. We're going to set temp equal to if it's less than it, we're going to do all of that. Otherwise, we're going to do all of this. So we're going to set, we're going to see if temp right is null, and it's not. Temp right points to a 50, right? So we're going to set temp equal to temp right. It's not null, so we're going to set temp equal to temp right. So we're going to change temp to be right here. And we'll go back up to the top of the loop. We'll compare our number to temp data. Well, temp data is 50, our number is 14. 14 is smaller, so we're going to fire this part of the code, which says if temp left is null, and it's not, temp left points to an 11. So we're just going to do this temp equals temp left. So we change temp to here. So that's our new temp. And then we go back up to the top of our loop, and we compare number to temp data. So one more time, temp data is 11, our number is 14, that is bigger. Alright, if our number was smaller than temp data, we would do all of this. Otherwise, we want to move to the right. So now we're going to say if temp right equals null. This is our temp node, temp right is null. So what do? We set temp right equal to new node. So we're going to set temp right, and we're going to point it to our new node, and we're going to return. So before we get into the detail, the bigger details, does this make sense so far? It's our search routine, right? We start at the root, we move either left or right at each spot. But instead of looking for a node, we're looking for a spot where there's no node available. We're looking for, you know, we should go to the left, but the left is missing. Or we should go to the right, but the right is missing. And then at that point, we simply change that left or right pointer to point to our new node. Okay, this will work fine with one detail. I don't know if it'll compile. Yeah, of course it won't compile. Look at all those errors, man. That's awesome. So let's be clean. Let's prototype. It's Let's Be Clean Tuesday. Man, I'm getting a lot of good errors. I don't know what my brain is doing right now. Can you tell I don't actually use typed Fs? That's an impressive number of errors from like one set of code. Passing argument 1 of insert from incompatible type. Alright. Those are pretty colors. I didn't even think it did colors. So tnode is a struct tnode. Alright, got that typo. There's a typo. At this point, I gotta make it work instead of just doing it the way I would normally write it, because, you know, it's a matter of pride at this point. Root. What the heck is root? Root is a pointer to, oh yeah, so, yeah. T-node. T-node, T-node. I honestly never use type defs, so I thought I would do that because I figured you might want to do type defs. But, alright, this is Sparta. Alright, so let's run test 1. And it's seg faults. So let's restart it. And let's step through it. So we're setting root to be null. Right. Now I want to go inside my insert function, because my insert function is what's going to throw the seg fault. So to go inside a function, I need to say step instead of next. So this will get me into the start of my code. So I'm going to set tnode equal to malloc. Sorry, new node. Right now, new node is null. After I call malloc, which I'm going to do with the next, new node is now pointing somewhere. And I'm going to set the left and right children to be null, and I'm going to set the data value to be num. And if I look at what new node is pointing to, it shows me really nicely. It's a structure. The data's 10, the left and right are null. That's what 0 is. Alright, so we've set that up correctly. Now I'm going to set temp equal to root, and I'm going to look at temp arrow data. Well, what is temp? Temp is null. Right? Why is temp null? Because my root was null. Why was root null? Because my tree was empty. And if I look at temp arrow data, it tells me you can't access memory location 0. That's the polite version of seg fault. Alright, so we have to deal with an edge case. So we've created our node. Is the tree empty? So if the root is null, then what should we do? If the root is empty, if the tree is empty, then the root should just become this one node that we're adding. So if the first thing we're doing is inserting 10 into a totally empty tree, what we want is a tree containing just a 10. So I'll do my tnode, I'll set new node left, I'll set new node data. I'll see if the root is null. It is, so I will set root equal to new node. So now root is pointing somewhere. If I look at what root's pointing to, it's pointing to my first node. So far, so good. Now I'm going to insert a 20. So I'll step into that. I'll set my new node to point to a 20 presumably, and I'll say if the root is null, and guess what? The root is null. So it's going to create a new tree containing a 20, right? And it's going to set root equal to that. So root's my node containing a 20, and it doesn't point anywhere. And I'll go back. And I'm going to insert a -5, and so I'll make a new node with a value of -5, and I'll check to see if the root is null, and guess what? The root is still null. So I'm creating these nodes, I'm setting root to equal to them, but the next time I go into insert, it seems to have forgotten about that. So what's the problem here? There's a 3-word answer, but I'll take a longer one. And this is what we were talking about at the end of class yesterday. What's the nature of the beast here? C is always passed by value. When I say insert 10 into the root of this tree, I am passing the value of this variable. Well, what's the value of this variable? It's null. And so when I call insert and I pass root, I'm basically saying insert parentheses null comma 10. And down here, it sets this variable root equal to null. But this variable root has nothing to do with this variable root. They're completely separate variables. And this is what pass by value means. When I pass a variable to an argument, the value of that gets passed, and this local variable is set equal to that value. But changing this variable down here, no impact on this variable up here. This is why when you call scanf, you have to put an ampersand in front of your variable, so that you're not passing, the current value of I, you're passing the address of I, and then scanf can go to that address and load a new value to effectively change the value of I. So that takes, various degrees of contemplation. But the punchline is, right, we can't change the value of this variable inside here and expect it to pass back to our main program. So we got two options. Whatever happens in a function stays in a function, exactly. So we've got two options, right? The first option is pass the address of root, and we don't want to do that because root is already a pointer to a T node. And if we pass the address, then we've got a, T node star star. And that's just going to be messy. So what we're going to do is we're going to change our insert function. The only thing is we need to get back the new value of root. So we're going to change insert to return a T node star. And then everywhere that we call this, we're going to say root equals. And this is going to be a T node star function. And when we return, we're going to return the root. All right, pretty minor amount of code we had to change, but fundamentally different behavior now. So now insert returns the root of the tree. And when we call insert, we pass it the root, but whatever it returns to us, we set root equal to that. And this is going to fix everything. Alright, so we'll start off roots equal to null. And we'll step into our insert function again. So we'll allocate space. We'll set the left and right children to be null. We'll set the number equal to 10. If the root is null, what are we going to do? We're going to set root equal to new node. And now, root is pointing to something. It's a 10 with null children. But we're going to say return root. And when we do that, our main program is going to do what? It's going to set its copy of root equal to what insert returned, which was insert's copy of root. So this is how we're passing our changes to root inside insert back to our main program's root. So now when I do this, I come back to my main program, and if I look at root, it's pointing somewhere. If I look at what it's pointing to a node with a 10 and no children. Alright, now let's go ahead and insert the 20. So I'll step into my insert routine. I'll create a new node pointing to the 20. So there's my new node. And this time it'll say if root is null, and it's not. Right? Root is pointing to this 10 node. So if root is null, it will do some stuff. Well, it's not going to do that. So it sets temp equal to root, and we're getting ready to move down the tree. So if our number is less than temp data, while our number is 20, and temp data is 10. So we don't want to move to the left, so let's step through, and it says, no, we're in our else statement. It didn't show us. But anyway, we're moving to the right, and we're checking to see if temp right is null. And it is, so we're going to set temp right equal to new node. Okay, let's look at what temp is first. Temp is our 10 node. That was the original root. And temp right is null. So we're going to set temp right to be new node. Let's execute that instruction. And now temp looks a little different. It's got a data value of 10. The left child is empty, but the right child is this interesting address. If we look at temp right and see what it's pointing to our 20 node. So we can go ahead and return that, and we're back here. There's our root, hasn't changed. There's what root's pointing to. Here's what root's right child is. There's our 20. Alright, so let's do a few more inserts. Let's insert our -5, let's insert our 11, let's insert our 45. And let's see what we've got. So our root is a 10. So let's make a picture of our tree. And the left and right children are pointing somewhere. They're pointing to these funny locations. So root left is this location in memory. If we see what's stored at that location, we see it's a node with a value of -5 and no children. So we've got a -5 over here. What about root right? So it's some location in memory. If we see what's stored there, it's a node with a value of 20 and left and right children. So we've got a 20 here. And let's see what's on the left. On the left we find a node with a value of 11 and no children. So we've got an 11 hanging here. And on the right, we've got a 45 with no children. So we have a 45 sitting off of here. So this is what our memory looks like right now. We have a pointer root which points to a 10, which goes to a -5 on the left, a 20 on the right, and that 20 has children 11 and 45. That's a binary search tree. And we built it up by inserting a 10, a 20, a -5, an 11, and a 45. And you can reproduce what happened. A 10 became the root, the 20 went to the right, the -5 went to the left of the root, the 11 went to the right here, went to the left, and went right there, and the 45 went to the right, and then went to the right again. And you can see where this arrow notation is going to start making more sense, right? This would be horrible if we were using, you know, star root dot right with a star in front and a dot right and so on and so forth. This just says, you know, start off at the root, see what it points to on the right, see what it points to on the right. If I want to see the data value of that, I can just do this. And it says start at the right see what it points to, look at the right of that, see what that points to, look at the right of that, see what that points to, look at the data. And if I do this, that should point to our 11. So this is squirrely, right? This takes more getting used to, but again, once you spend, you know, a few blurry-eyed nights doing this inside GDB and staring at your code and scratching your head and trying to figure out, you know, do I need an extra write in here or not, right? Once all of that connects, right, this is a really, really powerful way to analyze what your code is doing and to help debug it. All right, so what's your favorite number that's not in the tree already? 7 came up first. So let's insert a 7. I don't know if this will work. Hey, I think that worked. All right, so I'm tricking GDB into running code for me. Right, so I'm asking it to print something. What am I asking it to print? Well, the value of root, but I'm also asking it to set that equal to insert root 7, which is forcing it to call this insert code. So I think we've just inserted a 7. So let's see if we did. So if we print root left, it's this T node. If we look at that node on the left, that's our -5 again. But remember, before our -5 had no children. Well, now our -5 has a right child. So if we print the root's left child's right child, what do we find? We find a node with a 7. So that's this 7 that we just put right here. All right, second person in was a 13. So let's insert a 13. So where would we expect the 13 to end up? Right of the 11. So let's see if that's what happens. So root right points to a 20. That 20's left child points to an 11, and the 11's right child, there's our 13. So if we started the root and we go right, left, right, started the root, go right, left, right, there's our 13. And if there's anything weird going on, this is a whole lot faster once you're used to it than, you know, writing your code and adding printfs and running it and, you know, changing it and things like that. I mean, I'm right here. I can work with the memory directly, right? I can do function calls like this, and I can snoop around memory and so on and so forth. All right, so so hopefully this is making a little more sense than yesterday, at least, as far as returning the pointer to the node and setting root equal to that. Again, the only time this does anything is in this first statement. If in all of these statements I just called insert, that wouldn't matter because root's never going to change once it's not null, right? Every place that I return, I just return root. I return root. The only time root changes is if root started off null, and then I set it to the new node. But we keep a uniform structure. We just set it up so anytime we call insert, we take the return value, store that in root. So yeah, speaking of the remove function, right, this is going to get interesting when, for example, we are able to delete nodes. Well, if I want to delete the 7, right, I'm just going to change this right child to be null. -5 is right child, and that's fine. But what if I wanted to delete the 10? What if I want to get rid of this? I can't just set root to null, because now my whole tree is gone. I'm going to have to do something else. But whatever I do, the root is not going to be 10 anymore if I'm deleting 10. It's going to be something else. So when we delete, we're definitely going to have to change the root. And so there again, it's going to be really important that we do something like root equals, delete root comma 10. And we'll see this in pretty much every data structure we do. When we call a function to manipulate it, it'll return a potentially new handle to the structure. And we'll see this in trees a lot. Yep, hold on a second. Thank you. You too. Yay, packages. They tried to deliver yesterday and they didn't think I was here. So questions? All right, let's start talking about traversal. And we're not ready to write code for this yet because we've only got a few minutes. But we've got a tree that looks something like this, so I'll put back the whole tree. So let's say this is our tree and here's the root. And we talked about the idea of, to print this, we need to go down every possible branch. And it's kind of like running a maze, right? When we get to this spot, we need to remember that we could go left or we could go right. And if we go left, we need to remember at this point that, maybe we wanted to go left. And then we're going to end up going right. And when we're done with all of that, we need to remember where our finger was before, which was here on the 20, and that we had gone to the left, and now we need to go to the right. And so we need some kind of mechanism for keeping track of, where we are and where we need to go back to move in a different direction, right? Which was what we did when we ran mazes. We sort of put our finger down and said, okay, if I need to do something else, I'll come back here and I'll go a different direction. It's basically what we're doing traversing. And that basically calls for a stack. But there's an intuitive notion of how to look at the data in this tree. If I want, I can think of it as follows. So I want to print out, every node in this tree. Well, I could do this with 3 simple steps. Because this tree has 3 pieces to it. It has a root, and that root has a left subtree, and that root also has a right subtree. So printing the root, that's easy. That's just print root arrow data. But how am I going to print everything in one of these subtrees? Well, I'm going to find a friend who knows how to print trees, and I'm going to say, hey, here's a tree, can you print the contents of this for me? And they'll say, yeah, Nick, I got you. And they'll take this tree and they'll hand me back a piece of paper, and it'll say 10.5, 11, 13, 20, 45. And then I'll go to that friend and I'll say, hey, can you print the data in this tree for me? And they'll say, yeah, and they'll hand me a piece of paper that says -5 and 7. And then whoever asked me to print this tree, I just hand them a piece of paper that says, you know, -5, 7. I give them a 10 because that's the root, and then I give them the stuff my friend gave me for this, 10.5, 11, 13, 20, 45. So we're going to mostly punt. We're going to mostly take the task of printing this tree and hand it off to someone else, to another function. So to print all the data in the tree, we're going to do 3 things. First, we're going to print all the data in the left subtree, and then we're going to print the root data, and then we're going to print all the data in the right subtree. So yeah, this is recursive. Somebody else said it, not me. But this is going to be a recursive print function. But we can do it, you know, by hand with a stack. We can keep multiple fingers and say, you know, we're right here and go down here and come back and then go back to my finger and say, okay, let's do this, and I'll put another finger there and I'll come to the left and do that. And when I'm done with all of that, I'll go back to my finger and go to the right. Those fingers, right, every time we put our finger down, we push something onto a stack. And every time that we come back and we want to go in a different direction and we're done with, you know, what we were doing from this point, we're going to pop it off the stack. So we'll look at this using stack-based code tomorrow, and then we'll look at queue-based code and see where that gets us. And we'll come back to traversal in another day or two and start looking at recursion. But we're not quite there yet, but that's where we're going. All right, have a good one. I will see you tomorrow.